So yes, good morning, students. And today we'll be learning our first machine learning algorithm, which is a gradient descent. And this algorithm is perhaps the most influential and perhaps the most important one that you have to know because the modern deep learning architectures, transformers, large language models, computer vision models are all relying on this primary algorithm to do backpropagation. So it's extremely important that you understand that this first lecture. So let us take a look at the outline, what we will be learning today. So this is just a recap of the loss function that we learned in the class. It's basically nothing but the predicted y in which you input the x feature x at the sample I in some hypothesis function, and then you return a predicted y. You find the distance between your predicted y with your actual y for every I sample. And you square it so that the distance is being negative and positive distance means the same. So you square this. And 1/2, it doesn't really matter because it can be 1 over m, because when you find the derivatives, it does not really matter. We also discovered that if we want to find the optimal parameters for this hypothesis function, we can use gradient descent. And the idea is that if we can just follow the slope, if the slope is on this side, and if we go to the opposite side of this slope, which is on the left, then we can always go down. And eventually we will find the optimal weight in which the cost is, or the loss is minimized. At the same time, if you can imagine that the gradient is on this side, the slope is actually negative. But if you go to the opposite side, which is positive, you can also go down, right? So the idea is that if you find the slope of the gradient in response to the cost, and you go to the opposite direction of that gradient, you will eventually go to the optimal weights that reduce in result into the minimized loss. So firstly, because this is our loss function, which represent this axis, we have to now find the derivative of the weight in respect to this cost, right? So we simply use our calculus idea and find the partial derivative of the loss function in respect to the weight, right? And J here refers to each of the feature, right? So you have to imagine that we have weight for feature 1, feature 2, feature 3. If we are trying to predict some GDP, the egg price, the gold price, and the oil price could be each of the J, right? So that's why we have to find the partial derivative in respect to each of the feature. So here we just simply do the normal thing we do in calculus, and we found that the partial derivative of theta j in respect to the partial derivative of j in respect to the theta j is nothing but the hypothesis function x minus y multiplied with the x at feature j, right? So now we can plug this into the update algorithm, in which we say that the original theta simply go to the opposite direction, right? So we minus. So minus can always make sure that we go to the opposite direction of the slope, right? And we multiply with a number called alpha so that we sometimes do not overshoot, right? Because if we just take the slope, it can be some numbers like 100. And perhaps if we go to 100, if we go too much, we can go to this side, right? We don't want to do that. We want to go slowly down, right? So that is the idea, that we want to multiply with the alpha. And this number is typically something like 0.01 or 0.001. Now, because we have the J feature, we can actually make this a more elegant format by turning everything into a vector format, right? So imagine that this weight vector is a vector now. So you can imagine is a vector, it's an array of all the feature, right? And this is again, this is the original vector. And alpha is still a scalar, is still a number, but now x, right, become a matrix, right? And h and y become a vector, right? Because h is the predicted y of each sample, so it's a vector. So you can imagine an array. And y is the actual y of each sample, right? So you can imagine it as a one-dimensional array. But x, you have each of the sample, you have a lot of features, right? And the second sample, a lot of features, and the third sample, a lot of features. So x is actually a matrix, right? So if you try to work it out, you can see that this formula can turn it into this vector form. So now, this is just a recaps. And today, what we're going to do is try to take a look from the coding perspective to make sure that you understand what I'm talking about just now, right? Because mathematics could be slightly difficult if you don't have any mathematical background. So hopefully coding could help you out. So firstly, we're going to prepare some data, get your X and Y into the right shape. We're going to train and test your data, feature scaled, add intercepts. And then we're going to define our algorithm from scratch, right? So here we are not going to use anything like sklearn, but we're going to code from scratch. So coding from scratch is not something you would want to do in industry, but this is all for the purpose that you understand the algorithm by heart, right? And then we're going to compute the accuracy, and we can also demonstrate how we can actually use the final weights that we have obtained for final prediction. And this step we call inference. So let's start it. So firstly, why not we import everything we need. So is I'm going to use NumPy, and the version I'm using is 1.23.5. So to make sure that you don't really have to use the same version as me, but if you have come across any problem, then you will know that perhaps it could be the problem of the version issue. The next thing we're going to do is actually import matplotlib so that we can have something for plotting. And I don't think you can do this yet. So I'm going to do this. All right, and this is my matplotlib version. All right, so the next thing we're going to do is perhaps load some data, and then so let us try to do this. So we're going to do from sklearn datasets, import load data DVDs, right? And we're going to say diabetes equal to load diabetes, right? And it's loaded, and it's very important that we understand what it is, right? So we should print that out. And it seems like so if you see this, you know that this is a dictionary, right? But inside this dictionary, there's a lot of NumPy arrays data, right? So I would say that this is something like a dictionary of NumPy arrays, right? Right. If I'm not wrong, Python call this a bunch, and I'm not sure why they call that, right? So we're gonna comment this so that we save our. Okay, let me just put things like this so that we have we don't just jump like that, and then we can print some features, right? So we can say features, the PTs, the feature names, right? And then we can get that age. So this is something like some information about age, sex, BMI, blood pressure, and if I'm not wrong, S1 and S6 is some confidential information about certain matrix about blood, which I'm not sure what are they, right? But here it's not relevant for our lecture because we just want to predict something using gradient descent, right? So what else we can do? Oh, by the way, you for some of you may wonder how did I get this, right? Well, you just go to sklearn website and just look at the API. You should be able to take a look. Maybe I'm not sure you can see something of this, right? And you open the text editor and no, usually maybe one. Okay. So yep. So if you open this, okay, this is example, right? So this is a bunch, but we want to know this instead, right? So maybe we can try this. And here we can understand what is this function. And maybe we can open the text editors and we can see that feature names, right? So these are one of the attributes that you can actually use in this. So yeah, so make sure that you explored that question mark. Great. So I'm just gonna delete this, and what are we gonna do next, right? What I'm gonna do next is make sure that I have put this into this, and all right. So this is the data, and let us take a look, right? So firstly, we can take a look at the shape, and we got this 4, 4, 2, and 10, right? So you may wonder what are they, right? So typically 4, 4, 2 is basically the number of samples, right? And 10 is basically number of features. And then the number of features here is just corresponding to this 10, right? So we can say this is 6 and this is 4, so this is total 10. And we got 442 samples of containing 10 features, right? And typically in my class, we use this symbol m comma n, right? To make sure that you understand that m refers to samples and n equal to features. Most of the time, 90% of the time, all data set for machine learning should be formulated into this format. Otherwise, you won't be able to use sklearn or any other library. So make sure that you're very comfortable with this format. So now what we can do is we can say m equal to x dot shape 0 and n equal to x dot shape 1, right? So now we know that m is a number of samples and n is a number of features, right? Now, definitely, if you want to take a look at one sample, right, you can take a look, right? So here is sample 0, and these are the 10 features of that, right? So this could represent one person, right? Like myself, Chucky. So I have age 0 point something, and sex is 0.05, and BMI is this, right? So one thing you may notice, like Chucky, it doesn't make sense. Like, how can the age of a person 0.038? Well, this data set is pre-processed prior, so that's why it's already standardized. And I think we talk about why standardizing is so important, right? Because it allows your algorithm to reach convergence. A little bit of standardization I would talk more when we reach 1.3. So yes, so that is that, and we can definitely take the Y, right? And diabetes target, And again, we can take a look at the shape. Okay, so one thing you may wonder, like, oh, Chucky, why we only have 442? Why we don't have 10 here? Well, this is the things we want to predict, right? Is either whether they are having diabetes or not, right? So we don't really have 10 features. It's actually one. So in Python, you either put one here or you don't put anything, right? It's the same. 442 comma 1 or 442 comma, essentially they are the same, but Python doesn't understand in the same way, right? If you have one, is a 2D array. If you have blank here, it means this is a vector, right? So this is very, by the way, I use a small letter X, a big letter X to represent that, to represent matrix, right? So matrix is always two-dimensional. So there's an M and N, but I use small y because small letter y represents vectors, which is vector is basically a one-dimensional thing of array, and matrix is basically a 2D, 3D, 4D version of the array, right? So those are some names you may want to know. So we can take a look at the y. And this is basically based on this information. These are the diabetes. If I'm not wrong, this is not a classification. This is something like the blood glucose level, right? So typically, if you have more than 200, then you have diabetes. So great. One thing I can actually do is make sure that the m that I got from the x is actually equal to the y dot shape 0, right? Which this is actually known. You don't really need to do because this is a data set prepared by sklearn, so this by default sure. But I just want to show that by putting all this assert function throughout your work in the future is a good practice to make sure that your code does not break when you change something randomly, right? Great. So I think we understand this very well. So so now we can okay, give me 1 second. I want to close this, right? So great. And I'm gonna press M and then boop. Okay, so this is done. Now we go to the test trained split of your data. So what we're gonna do is simply split our data. Again, this is our data, right? So we want to split maybe 70% of the samples into training and 30% of this 442, right, into testing. So what we can do is you can do it manually. Like, for example, you can simply say that x train equal to x from 0 to, I don't know the number, like 300, then you will get all the things in there, right? But actually, sklearn also have this function called, and this is typically what students use, right? So x train, x test, y train, y test equal to train test split, and x comma y, that's size equal to 0.3, right? So once again, and then you can press enter, and what you can do is x train dot shape, and you can see that is now 309. And if you change to x test, is 123, y train is 309, and the y test is that. So it's automatically split it for you, right? By the way, you should not always follow how I code, just copy and code, right? You should try to see how did I know that this function takes in 3 arguments, right? And the idea is super simple, right? Like I said, you can either go to the website, or if you're in the you can just open this, right? And you can see that the signature is taking an array right, which is the x, right, and then the which is a series of arrays, right? So it could be x and y, right? 1 star mean tuples, 2 star mean dictionary, by the way, and test size is this, right? And none means that if you don't specify, it will be none, right? Automatically. So these are all default values. And definitely learn to, oh, this is very long, right? So learn to read this. If you don't like this look, you can always go to the website to take a look at the formal documentations. Great. So I think we got this. And so let us close this. The next thing we want to do is, by the way, I may not talk too much about why do we need to train and test split, because we already covered in the previous classes in the case study. But definitely it's only so that we can train our model using training set, and we should test our model whether it can generalize out on the unseen data set, right, using the test data set. Feature scaled. Okay, great. So even though our data set is scaled, I just want to do it for the sake of doing it anyway. So what we can do is sklearn.preprocessing, import standard scalar, right? And what does this do? Well, it's basically inherently what it does is that it takes every value minus the mean of that column, right? So let's say I have a one column of numbers 1, 2, 3, 4. What it does is that from 1, it would change to 1 minus, what is the mean here? The mean here is 2.5, right? Divided by the SD. So here I don't know exactly what is the SD, but it could be 1, right? Then the 1 will become and then the 1 will become minus 1.5, right? So those in what it does in the standard scalar, right? So what is standard scalar? Well, you just put everything into a more standard scale, in which once you finish this, the mean will be equal to 0 and the STD will be equal to 1, right? So that is what the standard scalar do. You may question like, why do we need to do standard scalar in machine learning? And the answer is pretty simple. Well, when you do this gradient descent, you need to update based on the direction of the derivative, right? If your numbers are very, very big, the direction will be very big. And even though you multiply with a learning rate, the updates will be very chaotic, right? So I think you can work the math out, right, in your head that when the numbers are very small, the updates tend to be more calm and easier to reach the bottom, right? So that is one thing why scaling allow you to reach faster convergence. Scaling does not give you better accuracy, right? This is a very important point because eventually, even though you don't scale, it may take you more epochs to reach the convergence, but eventually, if you do everything right, you will still reach the convergence, right? So scaling does not give you better accuracy, right? But it just basically reach faster convergence. Yep. So that is something you may want to put in mind. So now how do we do this? Well, we just create an object called scalar, and we just say that this is an instance of a standard scalar. And what we do is simply scalar.fit transform xtrain, right? So previously xtrain is this, right? Okay, this is very long, right? So we got to put to 0. So once we scale them, and then we also need to scale x tests. But the trick is to make sure that you transform based on the distribution of the train, right? If you fit transform using your own scale of the testing set, then there will be a lot of problem, right? Because you train your model based on training set, you should use the same distribution that it learns from the training set and apply to the testing set, right? So that it has the same scale basically, if you train your model using US scale, you should not test your model in the UK scale. It doesn't make sense, right? So you should use them into the same scale. Fit is basically let it learn this scale, right? But here I just use transform, so it does not, it just simply apply what it learned from the training and just transform X test, right? So we can take a look at the X train, and we can see that somehow this number changed to this, right? Actually, I don't really need to scale again because if I'm not wrong, this data set is already scaled one time, right? So if you scale one more time, I don't really know what will happen, right? So yep. And but now that I'm taking a look more closely, right? It seems like it's not really scaled with the mean of 0, right? Because everything looks 0.0, right? So perhaps the scaling is not done in the same way we do, right? But anyway, now everything is scaled to near the mean, right? Great. So I guess that's the steps, the 1.3. Hopefully you guys are okay. Everyone are okay with this. And then now we go to intercepts. So intercepts is very simple, right? If we have X, if our data is like something like 1, 2, 3, sorry. Like we have maybe two features, 4, 6, and maybe 9, 10, right? What we do is we need to dot with a vector, right? So we need to dot with a vector. So just give me 1 second. Sure that this is a comment. Okay, great. So you dot with a weight matrix of W1 and W2, right? So here, this is basically X dot product with the weight W, right? This is basically what it means by X at T, right? So now, so just give you idea. This is basically X at W, right? So this is the way you write it in the vector format, right? So this is so what do you do? Well, 2 times W1 plus 3 times W2, you will get the first number. 4 times W1 plus 6 times W2, you get the second number. And 9 times W1 plus 10 times W2, you get the third number, right? So that would give you a 3 number, something like, well, why not we just work it out, right? So, okay, so maybe W1 could be 2 and W2 can be 0.5, can be 1, right? So 2 times 2 is 4, 3, so 7, right? And then 4 times 2 is 8, 8 plus 6 is 14, and then 9 times 2 is 18, 10 times 1 is 10, so that is 28, right? So this is the idea of a dot product, right? So dot product is the idea that once we have the X, this weight will try to transform your X so that we can get Y, right? So this is the typical, hypothesis function in linear regression, right? And in our class, we learned something like theta tx, right? But this is in the vector format. This is in the matrix format. That is basically you just take a whole bunch and dot everything, right? So it's the same. So you may wonder, one thing you may also wonder, like why x is on the right and theta tx is on the left, right? Well, if I recommend you go home and try to do this. You will find out that this is the same as this one, but just for multiple sample. Yep. Great. So now what I want to say is that in linear regression, you also need to make sure that you have intercepts, right? So you need to have one more weight that is, so here should be W1. Right? But you should have an additional W0. Oh, sorry. I think something is wrong. Give me 1 second. Okay, great. So you also have W0, and this is the represent the weight for the intercepts. Okay. So how do we make sure that we always have this W0, right? Well, we just add an intercept of 1 here. Right? So now we have we make sure that our x has an intercepts, which can always multiply with W0, right? And for all these numbers, they are basically features. If you don't understand this, this is basically, this is the intercept, right? So if this is something like 4, the intercept will be always 4, right? Yeah. Right. So this is basically, if this is the x, right? So this is the, so let me just make sure that you understand this, right? So I think go back to the basic y equal to mx plus b. So here you don't know y, right? But for the first equation, m is this one, right? Right. M is w1 equal to 2. So this is a 2, and multiply with 2, right? And then plus the b, right? Because you set to 1, 1 might multiply W0. So the W0 will be always the intercepts, right? But this is only for one feature, right? What you need to have is that you need to also have this one, right? So plus 3 times 1, right? Something like this, right? So you can work it out, right? 1 times W0 is this one. 2 times 2 is this one. And 3 times 1 is this one, equal to one number, right? You put it here, right? So you can see that x and w actually is nothing but mx plus b, but it's just in the matrix form so that we can do it very effectively and efficiently. Just one operation, we get everything. I think you already understand a little bit, right? Just go home and try to work it out and you will be fine, all right? Great. So how do we do this adding intercepts, right? It's actually very simple. What do we do is intercept equal to np.ones x train dot shape comma 1, right? And so what does this looks like? So basically is a list of 1, and how many of them? 309 1, right? So if you wonder what are they, it's basically like this, just 1, right? And how many of them? 309, because it's come from the X train. And what do? We just say X train equal to np.concatenate intercept X train and axis equal to 1, right? And then if you print X train now, you can see that there's a 1 attached in the front already, right? Similarly, do this for S. So we're just gonna copy this. Right? And we're just gonna copy this as well. And now we're gonna just X test, and then that should be it. Yep. And now we can check now X tests. And now we can see that that's the one here. All right. So yeah, I think we add the intercepts already. Now I think we are okay to say that the first task is done. Whew. So we are done on the first. We are already halfway. Now we go to doing our algorithm, right? So let us define our algorithm. Okay, give me 1 second. I want to make sure that I can collapse this, right? So, okay, great. So firstly, what I'm gonna do is import time so that I can measure the time, and then assert xtrain dot shape. Right, to make sure that things are okay. And then firstly, we need to initialize the weight matrix, right? So what does the weight matrix looks like? So if x, so currently our xtrain.shape is like this, right? In which we now have 11 features because I'm adding the intercepts. How many weight we should have? Well, we should have weight W for each of this feature, right? So now we can simply say that the weight, or we call theta in our class, np0 x dot underscore train shape 1, because we have one W for per feature, right? So we just say that theta is a vector of 0. So we randomly initialize. You can actually also randomly initialize. It doesn't matter that you always start with the zeros, right? So this is a list of 0. And now what we're going to do is we're also going to declare a learning rate of 0.1. By the way, you can also call this alpha if you want to. That is corresponding to the things. And I'm going to declare max iteration of 50, which we're going to loop our algorithm. And now what we're going to do is we're going to say that, so there are 4 steps. 4 steps to actually 3 steps to gradient descent. All right. So number 1 is a prediction. And then number 2 is once you calculate the loss, you calculate the derivative or the gradient. All right. And then number 3, what do? You update the theta. Right. So how do you actually do prediction? Well, if you already understand, it's basically x at W. To calculate the gradient, if I'm not wrong, we already said in the above here that the gradient is nothing but x transpose h minus y, right? So x transpose h minus y, right? And to update the thing, we simply say that W equal to W minus learning rate times this thing, right? Which we're gonna call this grade anyway. All right, I think that should be clear. Now, why not we just define some function here, right? So firstly, we're gonna say that, okay, let us not define any function because I want to keep it in the simplest form. You can always define the function by yourself. But what we're gonna do is, firstly, we do x at theta, right? Right, and over here we're just gonna say x train at theta. You can try to dot here, right? So and see whether what it is, right? And you can see that it's all 0 because the theta is 0 and x train is what is the shape of x train? Right, it's 309,11, and theta shape is 1, 1. So when you dot it, this one will dot with this one, 11 will be canceled with this 11, and you will have only 309, right? So this is a very common way that you check what is the final shape of this, right? So now, and if you call this prediction, we usually call this y hat, and then you can now check the shape of this y hat, which is 309, right? So yep, I'm just gonna delete all this. Now we're gonna call this y hat, right? And so once we do the prediction, now we have some loss, right? So once we get the loss, we need to calculate the gradient right away, right? So how do we calculate the gradient here? Very simple. We just follow the equation, right? Gradient equal to x underscore train, all right, dot t, right? So t here is basically meaning the transpose of the version of the x train, dotted with h minus y. So h is basically the predicted y, right? So y hat minus minus y, if I'm not wrong. Yep, y train, right? And we can try to do this up here, right? And I think we already know, I don't know whether we have y hat or not, but let's try this. We don't have y hat, right? Because we did not do this yet. So why not we do this first so that we know what is happening, right? So this is basically the gradient, right? Once you do all the y hat minus y train, and then you dot it with this is the gradient. So you can see that for intercept, the gradient is this is a big number. For the first feature, the gradient is this. The second feature, the gradient is this, right? So what do you want to do? Well, you want to go to the opposite direction of this gradient, right? For each of the feature, right? So that is the idea. So again, I'm gonna delete this, right? So how do we update our number? Well, we just say that theta equal to theta minus learning rate times gradient, right? That's it, right? So now maybe we can take a look at what does this do. So previously, this is the old theta, right? So once we do this, we can check the new theta, right? You can see that there's some update, something happening, right? Which makes our number closer to the optimal, right? But you cannot only do this one time, right? Because you need, as the pictures show here, you need to do many times, right? So, but there's some things I also want to do. You see that the numbers is very big, right? So what I'm gonna do is I'm gonna make the learning rate 0.01, right? So that this number doesn't go too much, right? So this is also a very good trick to make sure that I know what learning rate I should set. So great. So I want to now put this into a loop, right? So what I'm gonna do is for I in range max iter, and then put everything on like this, and that should be okay, right? And we do this 50 times, right? And I don't need to know that. So let me check, right? So we don't really need this, right? Because we already checked. So we create a weight, we set the learning rate, we set the iterations, and then we just loop this many times, right? Maybe we should do something, right? We should say that how much time it takes, right? Time taken equal to time minus start, right? And then we also now want to print time taken, and we also want to print the final theta, which is this one, right? So we hope that based on this loop, so we can go down until we reach the optimal weight, right? So let us do this. And to make sure I'm very clean, I'm going to clear all outputs, restart, and then run all. All right, great. So it seems like it's very fast. So it's just that. And this is the theta. You can see that after I do many times, the theta now looks very interesting, right? Because there's some very unique representation distribution of all these weights, right? It's not just some random things, right? You can see that all these numbers seems to have a lot. So by the way, what is this meaning of this theta, right? Well, if the magnitude is higher, it means that feature is important, right? Right. Ignore the negative sign. So what do I mean? Well, if you can see that 145 is the biggest, right? The next biggest one is 27, 21, 17, and minus 9.8. So I consider this as high also because I just cut the minus, right? It does not mean minus or plus is minus mean not good. Minus means that this feature is just directly opposite of the target, right? So if this number go down, that number the y will go up, right? But still, this means that this is very important feature, right? Regardless of the negative or positive, right? So perhaps definitely y-intercept is very big, but we can say that this feature is very important, and we can actually remember what are the feature name, right? So diabetes dot feature names, and we can know that this is basically S5, right? So S5 is very important. How about blood pressure? Blood pressure is super important. See, 21. So it seems like very important. Sex. Well, this is very strange, right? Because I thought male and female are the same, but seems like I'm not sure what is the 0 or 1 here, but seems like certain sex has a higher chance of getting diabetes. Age, not so much, right? So that is how you actually interpret this theta, which is very meaningful. One more thing is that you can only use this technique when you make sure that your numbers are all scaled. Oh, sorry, are all scaled right here. Otherwise, you cannot use this technique because it means that your numbers are not like in the same scale. Then you cannot really know their contribution, right? So make sure you scale that. All right, good. So once we do that, now we want to know what is our accuracy or loss, right? So you have to understand that for regression, usually we use mean square error, right? For classification, which we're going to learn later on, we're going to use accuracy or something like more complicated, like we call precision, right? So, but today we are using regression, right? Because we are predicting a continuous value. So we're going to try to find mean square error. So let us try to define a function for MSE. So the MSE is simply you take the y, right? And what do you do? Well, we just take the predicted hat minus the real hat, and then you squared it because you don't care which direction you want. And then you sum them. And then you simply divide it by everything, right? The number of samples so that you get the average loss, right? So this equation is very, very similar to this equation, right? Basically y hat minus y square and then sum everything, right? And then you divide it by m, not 2, right? Here. So it just happened that mean square error has the same loss function as the linear regression. But anyway, this is the MSE. So what we're gonna do is now what we want to do is training MSE and testing MSE, right? So for training MSE, what we do is y hat equal to h theta x train theta. Okay, I don't have this function, right? Because I did. So what I just do is this one. Now I know that if I use this theta and input this one, this is the y hat for train, right? And then what I can do is MSE train equal to MSE y hat train. And y train, right? So what are we going to do here is print MSE train, MSE train. All right. Now, how about for testing? We're going to do the same, right? So, give me 1 second. Just going to put option here and then the, oops. Okay, great. S, and then here should be X test. And then here should be tests. All right. And here should be tests. All right. Hopefully I did not. So this is the real test, right? When what we want to see whether our work generalize. So here is it. So it seems like our MSE for training set is this and the testing set is this. So how do we interpret this? Firstly, there's no overfitting because our MSE test is not so far away from train, right? So MSE train. So this means that if our training set is this, we still get the same similar, right? Which is good. The question is, how do we make it smaller? Well, that is the question whether we should use a rather linear regression or some other algorithms, right? Like polynomial, for example. Great. But anyway, I think this is not so bad. Now, how much? So I think that should be it. Now, oh, I still have one more thing I want to do, but I can close this. We're going to do plot some graphs. So we're going to do import matplotlib dot pyplot sblt. Okay, to save my time, I'm just going to copy something I already prepared right away because I think the video is already getting long. And all right, and y-hat is not defined. And because I use y-hat tests, so I'm going to just boop, 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 y-hat tests. Okay, great. So this what this plot do is basically just plot the true values and the predictions. And if things lie on this axis, it means we are doing very well, right? So mostly I feel like we are doing quite well, right? For all the field. Okay, now comes to the part that is the most interesting, right? That is now we got our model. So what is our model? This is our model, right? The theta is our model, right? So we believe that if we got some numbers, we can always predict the blood glucose level, right? So how do we do this? Well, you can actually take a look at one sample. The one sample is look like this. Well, let's say my own sample could be some NP array of some random number like 3 minus 0.3. Yep, you can just copy this value, right? Because I don't have any idea what would be my sample. So I just copy here, right? And this is my sample, right? Right. And then what I do, well, if I have this sample and I have this theta, right? I simply my sample at theta. And then I got this blood glucose, 376, right? So you can use your algorithm right away. Now, let's see whether it's close to the actual one, right? So because we already take from x train 0, we can actually know the answer, right? We know that this is a y train 0. So the actual one is 181 and 376 is quite far, right? Well, because the linear regression is the simplest form of prediction. So that's why it does not like perfectly, but it's a good start, right? Great. So hopefully you have gone through all this linear regression. So let us do recap. First, we do this loss function, right? We cover how do we do derivatives, updates, and update vector form. If I'm not wrong, this is a little bit confusing part that you need to go home and work it out. But trust me, this is correct, right? And now we go through preparing some data. And we split our data, we feature scale our data, we add intercepts, right? We did not do any feature engineering because we plan to do it in the later future lectures. And when we fit the algorithm, we learn that there's only 3 steps, right? So gradient descent is actually very, very simple. But if you truly understand this, you will be very good. You will have very good foundation for your future work. And then you compute the loss here, and this is for training loss and testing loss, and we found that they're very so close by, which means that there's no overfitting, right? But we should do better, right? Because this is even though there's no overfitting, this looks like underfitting, right? That means it's too far from the good results. Yep. And then we plot some good graphs, and then we do some inference, which is the most important. And you may wonder, what is the model? The model is the theta here, right? In what you just start with the theta, and hopefully you can predict your blood glucose. Yep. Thank you very much, and see you in next video coding. Bye-bye.